In the last module, we studied the ArrayStack implementation of a list. In this implementation, the list elements are stored in an array A. Occasionally, A gets too full or too empty and has to be resized. To make things easy, we studied the efficiency of the ArrayStack operations by ignoring the cost of these resize operations. Now it's time to show that these resize operations don't add much to the overall running time. We'll do this using a technique called amortized analysis, in which we'll study the running time of a whole sequence of operations. For an ArrayStack, this means that we'll study the total time spent resizing when we start with an empty ArrayStack and perform a sequence of M add and remove operations. In particular, we'll show that the total time spent in calls to the resize function is only proportional to M. Although the cost of resizing varies from one add or remove operation to the next, this result tells us that the average or amortized cost of resizing is only constant. Recall how the resize operation works during an add IX operation. When we try to add an element and A is already full, we allocate a new array of size 2n and copy the n elements of A into this new array. After a remove operation, the array A may be less than 1/3 full. We handle this the same way. We allocate a new array of size 2n and copy the n elements of A into this new array. So that we can focus on a concrete quantity, our strategy is to study the number of elements copied during all calls to resize. This is good enough, since all the work done in the resize operation is proportional to the number of elements copied. We'll show that during our sequence of M operations, at most 2M elements are copied during all of the calls to resize. Now, consider the situation just before a resize triggered by adding an element. This happens when A is completely full. The length of A is equal to n. If we look back at the most recent resize operation, the one that allocated the current array A, we see that right after the resize operation, A was exactly half full. It contained exactly n over 2 elements. Since A now contains n elements, we can conclude that an additional n over 2 elements were added since the last resize operation. This means that between the previous and current resize operations, at least n over 2 add IX operations were performed. Next, consider the situation just before a resize triggered by the removal of an element. This happens when A is less than 1/3 full. N is less than 1/3 the length of A. Again, if we look back to the situation immediately after the most recent resize operation, we see that at that time, the array A was exactly half full. Since the difference between 1/2 and 1/3 is 1/6, we conclude that at least n over 2 elements must have been removed from A in the meantime. To summarize, it doesn't matter whether a resize is triggered by an add or remove operation. If the upcoming resize operation is going to copy n elements, then at least n over 2 add or remove operations have occurred since the previous resize operation. Now that we've established this, we can take a step back and look at an entire sequence of M add and remove operations. Some of these add and remove operations trigger a resize operation. Suppose that, during the ith resize operation, n sub I elements are copied. Let M sub I denote the number of add or remove operations between the I minus first and ith resize operation. We've already established that M sub I is bigger than or equal to n sub I over 2. There are at least n sub I over 2 add or remove operations that have to occur before the ith resize, but after the I minus first resize. Let's summarize. The total number of items copied by resize is the sum of the n sub i's. The total number of add and remove operations is at least the sum of the m sub i's. But each m sub I is at least half of n sub I. This means that the total number of add and remove operations is at least half the total number of items copied by resize. Another way of saying this is that the total number of items copied is at most twice the total number of add and remove operations. Since all the work done by resize is bounded by the number of items copied, we conclude that the total time spent in calls to resize is O of m. This completes the proof of our theorem about array stacks.